My name is Jakob Steiner. I'm a co-lead of one of the groups under React, looking into mountain risks in high mountain Asia, together with Adnan Siddiqui, who is also here today. I've asked Jakob Grahn, who's a scientist at NORCE today, to speak about snow avalanches. I know his work because we previously had some brief interaction when I was still based in Nepal, and he was providing excellent insights into technologies to monitor avalanches in Nepal. And there is a big demand for that in high mountain Asia, especially with radar technology or with SAR technology that is not so trivial to actually deal with. So I'm very happy that he agreed to talk about his experience and his work today here in the webinar. He did his PhD, he completed his PhD a couple of years back in Tromsø, and is since then a scientist at NORCE working specifically on avalanches, and last time I met him, he was working also with a group in Austria in Graz on avalanches there. Without further ado, Jakob, thanks again for joining today, and I would give the floor to you. The presentation isn't going to last for ages, so there will be time at the end for all of attendees to ask him questions, I guess. And I'm very much looking forward to the insights that you provide to us on snow avalanches today. Please go ahead. Thanks so much.
Yes, thank you. Yes, so as Jakob said, I work at NORCE. So first I'd like to just acknowledge that there's many other people that are working on this topic as well and are important for the tools that we use for this specific topic of snow avalanches. So I'm located in Tromsø in northern Norway and work at this place called NORCE. And just a little bit of background about what that is. It stands for the Norwegian Research Center. It's a non-profit research institute, and it's about 700-800 researchers. Of most people have a PhD degree. And NORCE is doing all sorts of science and research, of which remote sensing is one of many topics. And actually, remote sensing is kind of a big topic in Tromsø, where our group is located. And this has to do actually with the geography and the fact that Tromsø is actually very far now up north at 69th degree latitude. And the reason why remote sensing is a big topic here with quite a lot of industry and research centers focused on that is because most Earth observation satellites are in polar orbits, which means that they are very often seen the further up north or south you go. So if you want to communicate with these satellites, it's very good to be far up north. So there is a long history of this in Tromsø specifically. Another reason why I personally ended up in Tromsø is because it's quite a special landscape. I like mountains. I'm born in northern Sweden, where it's a bit more flat, while the landscape here is characterized by steep mountains and fjords. And this also relates then to the topic of today. This also comes with a danger of avalanches. Just to illustrate this with a tragic example that happened 2 years ago close to Tromsø, to illustrate the destructive nature of an avalanche, is this case that happened on Reinøya in March 2023, where a slab avalanche swept away a small farm. That the whole farm was swept out in the ocean and killed 2 people and a lot of animals. This kind of illustrates the destructive nature of this. And historically, there's many events that have killed a lot of people. So this talk is divided in 3 parts. So I will go into a bit what is a snow avalanche, how are they formed. Then I will talk about radar remote sensing, how that can be used to monitor avalanches. And then I will talk about one use case of using the type of data we produce, and that is to try to do better avalanche forecasting. which is currently a big topic here. So first, what is a snow avalanche? It's basically the result of an accumulation of snow on a slope. And if for some reason there is a reduction in friction within the snow, gravity pulls the snow down, which is basically the definition of an avalanche. And this typically happens, as a rule of thumb, if the slope is roughly more than 30 degrees. You can typically define the avalanche path into three parts: a starting zone where the avalanche is triggered, a track where it's moving, and then where it accumulates on a deposit zone or runout zone where you get the collection of debris. Typically, you can classify avalanches into four types. Loose snow avalanches that are the result of typically if you have a lot of new snow, or if the snow becomes wet and then the bonding in the snow gets reduced and the snow starts to flow down. This typically happens in very steep slopes and is usually not a very dangerous type of avalanche. In contrast, the slab avalanche is typically a much bigger avalanche, and they are formed due to some sort of fracture on a layer within the snow. These types typically happen above 30 degrees. They can be very big, and they can contain a lot of snow. And since they're gliding on a layer, they can also gain very high speeds. Then there's another one called gliding avalanche, and this is basically when the whole snowpack starts to glide on the bottom, which typically happens if you have somehow a smooth surface, like a grassy slope or a clean rock face, which also can be quite big and typically related to melt and accumulation of liquid in the snow. And then there is one called the slush flow avalanche, and this is quite different actually, and it is caused by a rapid increase in water content in the snow. And this actually can happen on very gentle slopes and typically happen, or they typically start where you have an accumulation of water, and then they can flow down more like a liquid on gentle slopes. So among these four types, if we look at kind of the most dangerous ones, this plot shows the fatalities in Europe that has been recorded, separated by types. Here we see that the most common type of avalanche that kills people is the slab avalanche. So this is kind of the most important one to predict and keep track of. Just to illustrate what this might look like, this is a video clip showing a skier skiing down a relatively not very steep slope. And up to the left here, you see that the avalanche is triggered. Although the skier is quite far from the avalanche, the skier is triggering this avalanche remotely. So in this case, there is a layer that collapses within the snowpack and propagates up at some point where the slope is steep enough for gravity to start to pull down the snow, forming the avalanche. You see how big area this can propagate over, and also how fast and big the avalanche can be. So a slab avalanche consists basically of three parts. You have some sort of bed surface that is consolidated snow. You have some sort of weak layer, and you have a slab that is also consolidated snow. And the way this weak layers forms is basically due to transport of water vapor within the snowpack. So typically water wants to move from, or any gas wants to move from areas where you have a high pressure to a low pressure. In the snowpack, it's typically, or one cause of pressure differences is temperature. So at a part of the snow that is warm, you have more water molecules sublimating from the ice crystals in the air, thus increasing the water vapor pressure. And this water vapor will try to move towards the colder area where there's a lower concentration of water molecules. So if you have a cold ice crystals on the colder bit, you will typically have a directional crystal growth towards from the cold to the warm part of the snow. So this can, for instance, happen if you have a warm ground and a snowpack and cold air. And then this kind of crystal growth can form at the bottom at the bottom of the snowpack or at some sort of ice interface within the snowpack as well, and form such a weak layer. Or it can have the case where typically at night the top of the snowpack is rapidly cooling due to radiative cooling. So it basically radiates away its heat, and it doesn't really heat up quick enough from the air that actually the snowpack can become cooler than the air. So in this case, water vapor will try to move from the air on into the snow, and thus forming these surface facets. And if you then have snowfall on top of this, this can form such a weak layer. Another process that happens within a snowpack is if you have no temperature gradient and you have some sort of ice crystals within the snow. This ice consists of a lattice of water molecules in this hexagonal pattern. So within the ice crystal or snow crystal, each molecule will be quite tightly bound by a lot of neighboring molecules. While if you look at the kind of the edge or a convex part of the crystal, each molecule will be more loosely bound. There are fewer neighbors to each molecule. And so more molecules will sublimate and be kicked off the crystal, become water vapor at the pointed bits of the ice crystal compared to the concave bits. So as time goes, you will actually have you'll have a higher pressure, water vapor pressure at the pointed bits and a lower at the less pointed bits. So gradually, water molecules will move from the high pressure to low pressure, forming more rounded crystals. So in the snowpack, you have kind of these two competing processes that are largely determined by the temperature gradient. That can basically form instabilities or making the snowpack more stable. In addition, wind is an important factor. So if you have a snowfall with low wind and then you have high wind, wind will typically make the snow more compact, and this can form like slabs on top of fresh, kind of weak snow called wind slabs. And in addition, rain can also be an important factor that it adds weight to the top of the snowpack, thus breaking any weak layers that might exist. And they can also affect the kind of strength of weak layers as such. So all in all, there are a number of drivers for snowpack stability and the occurrence of avalanches, including precipitation, wind, temperature gradient, and liquid water within the snowpack. So it's quite a complicated process to keep track of if you want to try to predict this. So some mitigation strategies that are used to avoid avalanches is either you can actively try to trigger them. In North America, they even use artillery for this. But you can also go out in the field and place explosives or put different kind of towers that are regularly depositing some sort of explosive on top on the slope to constantly trigger accumulations of snow. Or you can build barriers that basically tries to stop avalanches. But among these, the by far cheapest and most environmental friendly way to deal with this is to try to do forecasting, basically, and try to basically avoid the avalanche when they might appear. In Norway, it's the Water Resource and Energy Directorate, NVE, that is responsible for the national avalanche forecasting. And here it's divided into 24 so-called forecasting regions. And each forecasting region gets a danger level every day. That is a number 1 to 5, basically saying how much avalanche activity might there be for the next days. Now, if we compare this to, and if you zoom into the forecasting region of Tromsø, this is actually quite a big region, so it's more than 100 kilometers in size. And the challenge here is basically to sample the whole area. So it's hard to keep track of kind of the snowpack parameters for such a big area. So if you compare this to weather forecasting, typically a weather model is outputting data every hour. It's doing it on a much higher resolution. In Norway, it's typically at the 1 kilometer grid, and it's outputting many type of variables and forecasting variables. So one question is, why can't we do this also for snowpack? Like have such a detailed forecast for snowpack and avalanche danger. The main reason is that the observational data for weather is much more. There's a lot of satellites that are constantly monitoring the atmosphere around the globe. And these are then fed into the weather models and steer the weather models. Well, if we try to do this for the snowpack, we can't really. So we need to know like temperature gradient, details about layering, details about crystal structures within the snow. So how can you do this from satellites? It's if not impossible, it's very hard. So typically you need to rely on manual people going out in the field. Now, what we can do is to use satellites to monitor the events themselves. And this is what I will talk a bit more detail about now. And for this, we use synthetic aperture radar. So that is the next part of this talk, radar remote sensing. So just briefly, what is a synthetic aperture radar? It's a side-looking radar that is sending out coherent pulses, coherent meaning that you both have amplitude and phase within this pulse recorded. They achieve very high resolution. They do this by in the range direction, so that is in the look direction. You use pulse compression techniques, so you basically send out some sort of pulse that have a bandwidth. Typically, this is a linear chirp. Now, these pulses can overlap, and you can still separate them due to their bandwidth. So in range direction, you can use this technique to get actually very high resolution down to meters from a satellite. Now, in the azimuth direction, that is the flight direction, it's a bit more tricky. However, since the pulses are coherent, you can actually estimate the Doppler shift. So actually, you do get such a chirp also in this direction, just due to the fact that the sensor is moving. So in the flight direction, you will have higher pitch on the pulses, and in the kind of backward direction, you will have a lower pitch of your response. And by using this in the same way as in range compression in range, or pulse compression in range, you can actually increase the resolution also in azimuth or the flight direction. Additionally, so these use microwaves that penetrate the atmosphere, so you're not sensitive to clouds, which is very good for snow monitoring, where it can be quite cloudy. And in addition, you produce your own radiation, so you don't need sunlight as well. So it works also in darkness, which is especially useful for northern Norway, where there's a long dark winter. So compared to optical images, this is taken from Google Earth of some city. A radar image looks quite different, both in terms of the viewing, or like the imaging geometry. So here the skyscrapers tend to lean, and this is due to the fact that the pulses hit the top of the buildings before the bottom, so the geolocation gets a bit messed up. You also have effects that you don't see behind the buildings. You have shadowing effects, and in addition, the kind of the radiometry is quite different from optical images. So here you measure the backscatter. So the backscatter is basically the amount of radiation that gets scattered straight back to the radar. So suppose you have a flat surface, you don't get any backscatter back, while if the surface is rough, you get some backscatter. In the case of snow, the snow is transparent to microwaves, so you do get typically some response from the top rough surface, but you also get a response from within the snow from snow crystals, as well as layerings or the ground beneath the snow. The amount of or how far the radar waves penetrate depends largely on the amount of liquid water within the snowpack. So this graph shows the penetration depth of microwaves. So the solid line here is C-band, which is what we use typically. So if you add actually quite a little water, like 2% volumetric water content, there is a drastic decrease in how far the radar wave penetrates. And one paper that I think beautifully illustrates this is this by Brangers et al., where they put a C-band radar on a tower and let it monitor the snowpack throughout the winter season. And this is what this plot shows. So on the x-axis you have time, and on the vertical you have the distance towards the snow on the ground. So you see early in the season, before there is any snow, you have a response from the soil surface. And then as you get snow accumulating, you do get some response from the top of the snow, but still you have quite a strong response from the ground surface. And at points where you have rain, you do get a quite drastic change in the backscatter. So then you have a much stronger backscatter from the top of the snow. While when the snowpack cools down and freezes again, you do again get some contribution from within the snow and from the ground. So it's kind of a complicated mix throughout the season of surface scattering from within the snow, and also from the ground. While to the right here you see when the melt season starts, when the temperature rises and the whole snowpack becomes wet, you basically only get surface scattering. Yeah, and this is the paper where they show this. Now, yeah, so this is the case of snow. If you look at avalanche debris is characterized by like a massive increase in roughness. So typically you get a high response from the top surface, but you also have a compression of the snow, higher density, which also increases the volumetric scattering. Much less research has been done on the specific case of radar response from avalanche debris. So actually, the exact contributions from each part of this is a bit unknown currently. Yes. But yeah, the point here is that you get an increased response of the backscatter when you look at the debris, basically. And this is what we use to basically map out avalanches that have happened. The satellites we use, or the type of data we use, is the Sentinel-1 star satellite data. The reason for this is it's currently, I think, it's the only one that is working in an operational manner. So it has a fixed acquisition pattern and is continually acquiring data. And the data is free. And in the normal constellation, there are 2 satellites that fly like this, and they cover the Earth within 6 days. So each satellite have a repetition orbit of 12 days. The swath width, or the width of this type of data is 250 kilometers in the IV mode that we use, and the resolution is 10 meters. So you get quite a good aerial coverage and still get quite a good resolution with this type of sensor. And this illustrates the Troms Finnmark area in northern Norway. So what we do is that we compare the backscatter values between 2 passes separated by 6 days. And when you have an increase in backscatter, you see this avalanche debris highlighting. In this figure here below, the green color is indicating an increasing backscatter, and the purple color is indicating a decrease. And this particular example is showing this Reina example that I started with. So this type of data can be used for like historical validation. Like in this case, there was an avalanche covering the main road leading into Tromsø, actually covering a car with a man inside. And you can like get statistics about the size, like proximity to roads and things like this, which can be used also for like planning roads or planning buildings or planning deflection barriers if you want to stop avalanches, for instance. But what we are mostly interested in is to use the fact that you have a lot of satellite data, and we want to kind of scale this up and get a really large scale kind of view of the avalanche activity throughout the whole country. And for this, we need to automate this process. So we use machine learning for this. So we basically annotated a lot of examples of SAR data where we know there are avalanches. We've trained a deep learning model to try to outline these avalanches. And by this, we can scale up the process and map big areas. For the annotation, we've developed specialized tool for this. So it's quite a tedious process to kind of outline each and every kind of avalanche segment here. Currently, we have about 4,000 of these annotated examples. But we plan to try to outsource this both to NV, but possibly also to let users kind of crowdsourcing this process. Yeah, and we've developed different segmentation models based on deep learning for this, basically. And I will not go into too much details here, but there's papers on this. And we've actually tested many different types of deep learning models to do this task. As it turns out, actually quite many different architectures perform similarly well. So our take on this is that it's really the training data or the size of the training data set that is determining the performance more than the particular architecture you use. Yeah, so then you can deploy this on the Sentinel-1 archive and build the data sets, basically. And this data set that is shown here is actually available if you want to have a look at it online. You can see if it works. So if we go on to maps.norceresearch.no/avalanche, you see a visualization of such a data set consisting of 4 years, 4 winter seasons throughout the whole country, where you get kind of a good view of the avalanche situation. And this is also time annotated, so you can play around with it. So you get kind of a completely different perspective on the large scale kind of dynamics of the avalanche activity. Yeah, this is just a different visualization of this data set over spring season of 2020. Each year we find about 100,000 debris in Norway. Yeah, and one thing to keep in mind, and one kind of uncertainty with this method is that, as I said, the liquid water content in the snow is really kind of determining how much of the surface scattering you get. So in cases of very dry snow, surface scattering is still quite weak. And in some cases, it might be that even if you have a debris, there is not a significant increase in backscatter. Thus, they are more or less invisible. So we believe there is a bias towards wetter types of avalanches within this data set. And this also shows how this kind of data correlates to precipitation in this case, which kind of leads on to the next step in this talk, and is how can we use this for avalanche forecasting? Yeah, so basically we have a lot of data about weather, and we have now a lot of data about avalanche activity. So one approach could be to do forecasting is basically to skip the step of trying to say something about the specifics of the snowpack, but do some sort of data-driven approach where you look at meteorological and snowpack inputs and try to directly predict avalanche activity. So using satellite data, we can do this time series of avalanche segments. So given some sort of patch on ground, you have this history of avalanche activity. In addition, you have the topography in a dam, and you have some sort of meteorological variables from a model, and you can also simulate snowpack variables into this. Or schematically, it's viewed like this. So you have some sort of past history of this in time. If you then stick a meteorological forecast on top of this, all these inputs are known. You can try to predict the corresponding avalanche activity given this meteorological forecast. And by this, you get some sort of forecast about avalanche activity. And this is a big activity currently. And here again, we look at data-driven approaches based on deep learning. A challenge here is that the characteristics of each input type here is quite different. So typically, so the avalanche data, we have a 10-meter resolution, but they're sampled every 6 days roughly. While the meteorological data is very highly sampled in time, but lower resolution in space, and the dam is static. So what this model is trying to do is basically to massage each input here into some sort of feature space and then do prediction on this feature space. So this is a sketch that we work with now. We're still producing the training data for this model, and hopefully we will have relatively soon some outputs of actual avalanche forecasts given such a model. One drawback of using data-driven models like this is that it's kind of a black box, and it's if you want to use this in a real situation and do forecasting, it's important to have some sort of trust in the model. So explainability is one topic that we also look at. In this model, this is built into the model itself through something called cross-attention, which is basically something that is given past avalanche activity. It tries to steer the past meteorological data through something called attention, basically. I think it's easiest to visualize this. So these plots show different types of meteorological variables. And this attention is basically the colored lines you see here, where the model is kind of putting more emphasis on certain variables in time. And by looking at this, you can get a feeling for, given some prediction, you can look at, okay, where in the past meteorological time series is the model actually looking, and does it make sense to what we think is happening in the snowpack? Yes, but this is still ongoing research. So to summarize, yeah, we talked a bit about snow avalanches, what they are, how we can use radar remote sensing to map them, and then one use case where we try to use this kind of data to do and really utilize the size of the data set to use data-driven approaches to avalanche forecasting. But there are, of course, many other aspects where you can use this data. As Jakob mentioned in the start of this talk, there are other regions in the world which are even more remote than in Norway, where you struggle to get a full-scale picture of the avalanche activity, like in the Himalayas. And then to use this data, we also would like to get a better insight into what are the biases towards possibly wet type avalanches and so on, which is also currently a topic of research. So with that, I would like to thank you for listening and also I'd like to say thank you to the funders of this research, which is ESA, NV, and the Norwegian Space Center. Thanks.
Thank you, Jakob, so much for the presentation. I'm impressed by a couple of levels, but especially that you're so far into operationalizing this work, right? Because I mean, doing science on certain topics is one aspect, but then actually getting to work the inside with something as state of the art as the CNN that you have used here, and in general deep learning into a state that can be used for practical applications. That's impressive. We have, as an example in high mountain Asia, for example, we have been trying to advocate for a long time that there should be put a lot more focus on avalanches. But the people who die from avalanches in high mountain Asia are a factor 10 higher than from glacial lake outburst floods, for example, which receive a lot more attention, right?
Okay.
So avalanches are a huge issue. And I think the examples that you also brought from Norway are great. This affects people who are going to work, right? So these are roads affected, school buses going somewhere. So this is not just skiers. You showed the video, of course, of the skier, and in high mountain Asia, we are always trying to make the argument that, of course, so Europeans have this imagination. Sometimes this is just for cross-country skiers who kind of make a conscious decision for risk taking. But in high mountain Asia, and I think also many examples in Norway, these are people who are affected in their daily lives, which makes it all the more, I think, important to provide solutions to minimize their risk. So yeah, thank you very much for providing an insight in what is possible in this direction. There are already a couple of questions, and anyone who still has questions, please post them in the chat, or I guess in the Q&A. Meanwhile, I will read out the questions that are already there. I think the first
I
one.
cannot see them, or can I? No.
I,
Just read them.
I think they are in the general chat, but so Irena was the first one asking, do you have some values on how accurate the approach is in terms of identifying avalanches using deep learning? How many false alarms do you have, and what could be the reasons for false alarms?
Yeah, we have numbers on this, and it's partly published in this paper where we used the UNet, or the type of UNet. I don't have these numbers in my head. Part of the problem of assessing how accurate it is that most of the data we use is based on SAR. So the cases that are not visible within the SAR, we don't have in the training data set. So this is one kind of issue when you try to assess the accuracy. Yeah, and then there was another question apart from the accuracy.
Well, just what could be the reasons for the false alarms?
Yeah, reasons. Yeah, any kind of increase in backscatter that is looking like a patch in slopes are typically misclassified as avalanches. And this can be if you have farmland, for instance, where you have little snow or no snow, and you have like a truck driving on a field or something. This could possibly increase the backscatter. You can have clear cuts, for instance, and these kind of things. So typically, if there's a patch like increasing backscatter, that's the typical false alarm.
Okay, thanks. So then another question by Karan Shah was, what's the size of satellite data you have used for training? Can you tell some number of satellite images you needed, or some dimension to make it?
For training the segmentation model, I presume, is about 4,000 image patches, but each image patch is like something like 5 by 5 kilometer. Yeah.
Adnan Adnan, do you want to ask a question yourself? Otherwise, I'll read it out. Adnan is asking, referring to the cross attention slide, what do the colors represent? Is the figure for a selected feature from the deep learning model, or somehow for the entire deep learning network?
So that I can go back to it. This is per input meteorological variable. So it's only showing the kind of cross attention as the color here. It does not show the output of the prediction. So it's part of the kind of, you can look at attention as some sort of adaptive weighting of some input. So in this case, it would weigh more importance to the highlighted areas here in the metrology. So this is kind of based on some sort of mock-up. It's not based on it's not trained on the full data set that we will use. But we expect it to highlight, for instance, certain, if you have big snowfalls, for instance, or if you have some heavy rain. Yeah, so we can kind of quality control if the network is doing something that makes sense. So we use it as some sort of explainability metric. Yeah.
Great, thanks. So Francisco Lamosa is asking, have you noticed variations in surface roughness across the winter season? For example, you have midwinter thaws followed by snow recrystallization. At least that's an issue in Canada. And does this affect the performance of the model?
If you for some reason have roughness increases locally, like from possibly certain wind features locally, that could be a problem since it might increase the backscatter in some sort of patch-like feature. If you have a general increase in the roughness, you wouldn't kind of see. So the segmentation model looks kind of at shapes, so you wouldn't really see the kind of shape of the debris. So that shouldn't be a problem.
Okay, Abhishek has his hand raised. Abhishek, do you want to ask a question live? Or if you want to type the question. Meanwhile, I'll read out the next one from Irena. Would it be possible to generate the annotations now done manually with deep learning? This would help to reduce the effort.
Yes, that's actually something we have a master student working in Milan doing this to speed up the annotation process by having a model doing a prediction, and you basically just say yes or no. Is it a good annotation? The way I've annotated this is to use some sort of, I have like a drawing board. So just to speed up that process would be very valuable and something that we look at.
All right, thanks. There were more general question. Rajesh was asking if you can share the paper where that you showed as part of the presentation. If you have it at your fingertips, and I will try to Google it in the background. We can put the link, I guess, in the in the chat as well, or I'll post a link to your.
Yeah, I can provide some links to papers. A lot of this is actually not totally published yet, so,
Yeah.
but hopefully soon. But there
But yeah,
are some
well,
papers
I
on. Yeah.
I would encourage also those who are in the presentation to, well, you see the Jakob Grahn's name, and if you check back on his profile online, you should be able to find those as well. And the talk will be is recorded and will be available on the YouTube channel afterwards, so you're able to rewatch and I guess catch the links, the paper titles that you provided before as well. One more general question, goes in a different hazard direction, is how can I use SAR in terms of glacial lake outburst floods? Any insights that you can provide? I don't know if you have experience in this direction with other hazard types with similar technologies, Jakob?
I haven't really worked with glacial lake outbursts, but I would guess maybe you can see it in the SAR image, or like typically if something strongly deforms roughness or like the structure of ground, it will affect the backscatter. But I'm not really familiar with the glacial lake outbursts. But there are many kind of application on glaciers and also we have people here that work with glaciology and like look at interferometry and velocity fields and looking at subglacial lake movement of ice and things like this. So it's quite a versatile tool, SAR.
Yeah, thanks. I think also that so one issue with is the quantity of the hazard types, right? So with avalanches, you have quite a large amount of events happening, while with these glacial lake outburst floods, one issue that we have is a bit of a needle in the haystack. I mean, there are so few of them happening that it becomes much more difficult to train something as well. But in general, yeah, so there are approaches with SAR as well, also trying to track glacial lake outburst floods. One more question from Adnan. Do you think the same deep learning architecture or something similar can be used to train over interferometric coherence? Have you attempted it?
We haven't looked at coherence actually, but it's been kind of on my list to use it for the segmentation. Typically at C-band, you have very low interferometric coherence in snow overall. But if the snow is very dry, it could be that you still have some coherence, or over time, if it's wet for a long time, I guess you could have a high coherence from if it's like surface scattering. But yeah, so shortly, we haven't looked at it, but it's certainly interesting. It would be interesting to look at more.
Great, thanks. And Irena is asking, would it be possible to detect avalanches with INSAR techniques?
I mean, I think in terms of coherence, it would be interesting, especially also with L-band, where you typically will have a better coherence even if it's snow. But if in a debris area, I would assume that you lose all the coherence because it's like large deformations and much more than a wavelength, and a lot of kind of presumably volume scattering that is messing up the coherence. So in terms of coherence, maybe, especially L-band, but like to do displacement monitoring with INSAR on Avalanche, I don't think that is possible.
Thanks so much. I don't see any other questions in the chat. Is there, if anyone else has, yeah, so Irena says, yes, she thinks that L-band would be great for this application. I think there is still a lot of room to explore, right? It's in terms of technology, both in terms of technology, but also in terms of gathering more data. This is something that you've shown this for Norway, that you have an inventory of observations as well. We don't have something like this for many regions around the world in terms of training such a model. And then, of course, I think what we also saw for the applications you tried in Nepal is that because climatically we have a different situation again, right? The avalanches do look quite different, for example, in this monsoon regime. And then the question is again how transferable, I guess, training data sets are from one region to another. So, all those who are still in the audience, I guess there is still a lot of room for contributing to this also in other regions to make these kind of models more robust elsewhere.
I think Himalayas would be really interesting to look more at in terms of this.
There is another question now coming from Abhishek. In your slides, you have shown us that you used causal AI for enhancing the interpretability of the deep learning, but it's a little bit different from explainable AI. So have you used both causal and explainable AI already? And in which model have you used? Rubin model or a structure causal model? Is that something, a direction that you can?
So these attention masks are kind of causal in the way that they look backwards, but also the CNN encoders are causal in the way that they have a look backwards. So this attention is not necessarily used as explainability. It's kind of an important aspect of like transformers that are popular these days. So it depends, I guess, a bit what you mean with explainability. So this kind of cross attention can be used to explain certain aspects of the prediction. But then you also have, I mean, you can, there's many other explainability techniques that you employ on top of a model, like grad cams or integrated gradients or something like this for a classifier or an image classifier. These things we haven't used for these models. We have used them in another project where we looked at classifying polar low pressures on SAR images. But like the kind of how to put it, explainability techniques you use on top of an existing model we have not looked at. If that answers the questions.
I guess, Abhishek, I mean, you can say if that answers the question or if you have any follow-up. But in general, I mean, thank you very much for also for all the answers that you gave now to the different questions. I feel like someone said in the chat already that the talk was very lucid and the explanations were very lucid. Also to people who are not so familiar with the backend architecture and with the methods that are used in these approaches. I am a friend of webinars that don't go on forever, so I'm not. If there are no more questions around, I would be very happy to slowly close this as well. If no one else, also perhaps from the panelists or Irena or Adnan, if you don't have any other comments or questions. I learned a lot. Thank you so much, and yeah. So Jakob, for taking the time and explaining this topic to all of us.
Thank you.
And to all those in the audience who did not manage to, well, there were nearly 50 people around. Anyone who did not grasp everything or wants to share it with people who did not manage to attend the talk will also be available on the YouTube channel.
Out if anyone is interested or have questions, also just email.
Yes, thanks. Yeah, thanks, Jakob, for that offer as well. Yeah, to all those. But you see his name. He's very easy to find. If you Google him, I don't think you find a second person who works on Avalanches. So please do ask him directly if you have further questions in this direction. So if there are no further, I don't see any further questions, and no further comments from Irena or Adnan as well. So I'd be very happy to close this. Thanks so much, Jakob, for giving the talk. I'm sure I will reach out in future, as this is a topic that we'll have to deal with in high mountain Asia, definitely, and we'll need this technology. We cannot just rely on the optical data we have used so far. So thanks so much to you for giving the talk, and thanks to all the audience members for sticking around.
Thank you.
Have a nice day, everyone.